it both ways. You can move from one vertex or from the other to the other vertex. So if we look at the one I'm about to circle here on the screen, so this is the directed graph we are talking about here. And if you look at the edge of this particular endpoint of vertex, you realize that we have an arrow that points to it, meaning that the direction or the flow is only from A to B. The reverse is not possible. However, we have what we call a loop on a graph as well, which basically means that you can move from a vertex and then come back to the same vertex. So B and C happens to demonstrate the loop structure on the, and then also we have from B from A, C in that direction. So the directed graph means that it's only, the path are being defined using arrows. That is from one vertex to the other. The flow could be that way, but then the opposite will not be true. And for the undirected graph, the one we have to the far right here, there are no directions showing the flow of movement from one vertex to the other. That means that in either way, you can move in that direction. So you can move from A to B, and I think I come from B to A to B is the only possible direction that we can move in. So that is the difference between the directed graph and undirected graph. But then before we move on, let's look at some terminology that we can use in the theory. So for every single graph, each edge connect two different vertices, and no edges connect the same pair of vertices. That is an example of more like a simple graph. Each edge connects two different vertices, and no two edges connect the same pair of vertices. That is an example of a simple graph. And then we have multi-graph, which basically means that it can have multiple edges connecting the same two vertices. And let me use the example here to demonstrate that. So we have multiple edges connecting the same vertices. So assuming that these two are our vertices, B and then C, that means that we could have two edges that are connecting those let me say two vertices. So if you had to consider this, so probably another one could move from here up to this point. So this is one of the edge, and this is one of the edge. However, they are connecting the same two vertices. That is a multi-graph. And then an edge that connects to a vertex to itself is what we call a loop, just as we saw, just as we saw over here. This edge literally connect back to the vertex C. So this edge is called a loop. And then you can also have a pseudograph, which include loops as well as multiple edges connecting the same pair of vertices. So if you have a loop and also you have multiple edges that connect the same vertices, we call that one a pseudograph. Please, any question? All right, so let's look at some characteristics of graphs, especially with the undirected graphs. So two vertices, let's say U and V in an undirected graph G, are called adjacent or neighbors in G if there's an edge E between U and V, such that an edge E is called incident with the vertices U and V, and E is said to be connected to V. And then another definition for or characteristic for the directed graph is that the set of all neighbors of a vertex of V of the graph G V of E denoted by N of V is called the neighborhood of V. That is, if A is a subset of V, then we can denote it by N of A, the set of all vertices in G that are adjacent to at least one vertex in A. That is one of the characteristics of undirected graph. And then also we have the degree of a vertex in an undirected graph is the number of edges that are basically connected to the vertex. So number of edges connected to the vertex is basically called degree of the vertex. Except that the loop at the vertex contribute to 2 of the degree of that vertex. So let's understand this definition from this graph here. So consider this undirected graph here. So the degree please, can you see the screen?
No, please.
All right, so let's consider this graph here. Oh, just a minute. Please, can you see it now?
Yes.
All right, so the one I've just circled, that is the undirected graph. And when we talk about so when we talk about degree of vertices, this means how many edges are connected to a particular vertex. So looking at this one here, for instance, this vertex D, it has a degree of 2 because there are only 2 vertices, edges that are connected to it. So we have 1 here, and then we have 2 as well. But then as I was saying earlier, if you have a loop that contributes to 2 of the edges. So considering this particular C here, for instance, so we have one of the edge, 2, 3, 4, and then this loop will contribute to 2. That's going to make the degree of the vertices 6 for this particular directed graph.
Hello, sir. Hello, sir.
All right, so let's move on to the next.
Hello, sir.
Hello.
Yeah, please, I can't see the screen.
The screen has gone off, please.
Hello.
Hello, sir. We can't see your screen or what you've explained. We didn't see the screen. It came and went off again.
Okay, just a minute. Hello. Please, can you hear me?
Yes, please. We can hear you, but the screen is not showing. What you just explained, we couldn't see the screen.
Oh, okay. Just a minute. Let me. Oh, okay, just a minute. Please, can you see it now? All right, so what I was saying is that when we talk about degree of a vertex, it basically means that how many edges are connected to that particular vertex. So as I was saying earlier, considering this particular undirected graph here, and then taking this vertex D, how many edges are connected to it? Here we have 1 and then 2. So vertex D, only 2 edges are connected to it, and therefore the degree of the vertex is 2. When we consider C here, the degree of vertex C is 3 because it has 3 edges connected to it. So we have 1, 2, and then 3 here. And then the issue is that if you have a loop on that same edge, then we start, it will contribute to 2 in that scenario. And therefore, if we are to add another loop here to the vertex C, so this then to it like this one here, then means that this particular loop is going to contribute to 2 of the vertices, I mean the edges, or contribute 2 degree of vertex to the already existing ones. Earlier we had only 3, which is this 1, 2, and 3. But since this loop is going to contribute to 2 more, that means the degree of vertex for C is now going to be 5 instead of the 3. That is basically what I was talking about when you were not seeing the screen. All right, so we can move on. So let's take this example and try to understand what we just said earlier with the neighbors and the rest. So this is a non-directed graph, and then we are asked what are the degree and neighbors of the vertices in the graph G. Please, are we clear? What are the degrees and neighbors of the vertices in the graph G? So for every vertex, we count a number of edges connected to it, and then we write it down. So considering this vertex here, this vertex A, the number of edges connected to it is 2. So the degree of vertex A is 2. Similar degree of vertex B is equal to the same degree of vertex C, the same for vertex F, and all of them are 4, 4, 4 each. So this is F here. Number of edges connected is 1, 2, 3, and then 4. So the same applies to vertex B and vertex C. However, the degree of vertex D is just 1 because it's only one edge that is connected to that particular vertex. Please, are we clear? And also moving on for vertex E, it has only 3. And then the degree of vertex G, which is this one here, is 0 because there's no edge connected to it. Please, are we clear? All right, now let's move on and talk about the neighbors. So for N of A is B and then F. Remember, it's supposed to be a set. So unlike these ones that we have here, as degree of A is equal to 2, the neighbors are supposed to be a set. That is why we have the curly braces and then they're all written inside. So neighbors of A are just B, B, and then F, as we are seeing on the screen. And then also neighbors of B, neighbors of B are also A, C, E, and F. That's basically to say that how many vertices or which vertices are directly connected to the given vertex. Those happens to be its neighbors. And when we take the vertex A, for instance, we realize that it is only B and F that are directly connected to vertex B. So that becomes, or those becomes its neighbors. And similarly, if you take the neighbors of B, how many or which vertices are connected directly to B? So we have A, we have A, we have F, we have E, and then C, and then we have E as well. So those are what we just listed over here. And the neighbors of C also B, D, E, F. And the neighbors of D is only C. So it continues up to here. So neighbors of G is an empty set, or you can call it a null, because there's no neighbor connected or associated to this particular vertex over here. Please, are we clear?
Yes, please.
All right, so here's another example that you have presentation, just to look at how it works, right? But remember, as I said earlier, if there's a loop, then it contributes to 2 of the degree of vertices. And considering is your hand is up.
Thank you, sister. Like if I understand the previous diagram,
Okay.
meaning the degree of a certain node is equal to the neighbor of that particular node.
Not
Because,
well, you can say that. You
like
can say it, yeah.
Okay, because if
You can
the
see
A is 2, and when we come to the neighbor, we have the neighbors to be 2. I think is equal, and the last one to be G is 0, and when we look up to the neighbor, it's empty set. So I think
yeah, yeah, that's true. That's true.
Okay.
All right, thank you so much. So we can equally say that as well. Yeah. All right, so we have another example here that at your free time, just look at it. But then take note of the on vertex B, because it has to contribute to 2 to make the degrees complete. All right, so let's look at another theory, which is the handshaking theory. So if a graph G axis and then edges a non-directed graph with M, V belongs to V. That is, the vertices are all in the edges that we have. So this is what we call the handshake theory. And this is the proof of it. So each edge contributes twice to the degree count of all the vertices. And hence both the left hand and the right hand side of this equation equals twice the number of edges that are available. And then you can think about the graph where vertices represent the people at a party and an edge connect two people who have shaking hands. All right, so this is one of the theory that you can find in undirected graph, which is the handshaking theory.
Hello, sir.
Hello.
Yeah, your screen was off.
Is it the same for everybody?
Yeah.
Yes, sir.
Yeah, it's still off. It's still off.
Yes, still off.
Let me reshare again and see if it will work this time. Please, can we see it now?
Yes, please. It has come now.
All right. So another theory that you can talk about is this is specifically to undirected graphs. And for an undirected graph has an even number of vertices of O's degree. An undirected graph has an even number of vertices of odd degree. So the proof is if we let V be the vertices of even degree and V be the vertices of odd degree in an undirected graph, GV of E with M edges, then we can get this particular formula from it, right? Which is 2M is equal to the summation of the degree of vertices, which is also equal to the summation of degree of vertices plus the summation of degree of vertices. However, the first one is the vertex 1 over here, and the second one is the other vertex here. And they must be even since the degree of vertex is even for each V which contains the various vertices of V1. And then also the sum must be even because 2M is even, and the sum of the degree of the vertices of even degrees is also even. Because this is the sum of the degree of all the vertices of the odd degree in the graph, there must be an even number of such vertices. So this is also the theory 2 for just undirected graphs, which is a non-directed graph has an even number of vertices of O's degree. All right, so let's talk about directed graphs as well. And for a directed graph, GV of E consists of V and then a non-empty set of vertices or nodes. So at least for a graph, you should have either a vertex or vertex and node, but you can't have only an edge and then you call it a graph. But then if you have only a vertex, it qualifies to be a graph. That is why we are saying that for a non-empty set of vertices. So at least you should have a vertex in the graph. And then the edges as well. So a set of directed edges of arcs, and then each edge is an ordered pair of the vertices. And then the directed edge U of B is said to start at U and end at V. That is the direction that you show. So if it is a directed graph, then when you have the edges UV, it means that you can only move from U and then you end at V. So assuming that you are given a set of vertices and edges, and then you are asked, this is, representation of a directed graph. So draw the graph. It is very important to notice the arrangement of the vertices. The vertices. So this is V, a U of V, which means that the direction is only from, it starts from U and then it'll end at V. But if it is open and there is no restriction to which type of graph it is, then you can just move ahead and do V, U, or any other direction. But for us to be able to know that this is a directed graph which starts from U and ends at V, that is where we normally show the arrow of the movement from vertex U to the end of vertex V. So we can say that let UV be an edge in the graph G. Then U vertex of this edge and is adjacent to V. And V is the terminal or the end of the vertex of this edge and is adjacent from U. And so the initial and the terminal vertex of the loop are the same. The initial and terminal vertex of a loop are basically the same. So if we have this particular vertex over here, and we have a loop that's connected to it, and let's say the vertex is C.
Sir, it's gone again.
So the starting and the ending graph is the same. That is where we are basically.
Sir, it's gone again.
Oh, okay. What is happening now? Oh. The initial and terminal of a loop is the same. So I was using this to explain. This is a vertex that we have C. And then it has a loop which is like this. So since the initial and the terminal are the same, it means that C will map to C in that particular order. However, if it is a different or it's not a loop, then you have to find the initial vertex and the terminal vertex so that you can connect them with the edge. All right, so let's talk about the degree of directed graphs. However, in this we have two concepts that we need to consider. We have the in degree of a vertex when it's a directed graph, and then the out degree. And basically what we mean by in degree and out degree is that how many edges are connecting to that particular vertex, and how many vertices are connecting outside of the vertex. So those edges that are coming into the vertex are what we call the in degree, and those that are moving out are what we call the out degree. So let's consider this vertex over here. Please, I hope the screen is showing.
It is gone again.
So let's consider. Let me exit the meeting and join again, probably to work this time.
Okay.
Right. Good morning, Charlie. Sorry for the interruption. Let's hope the network stays correct now. And I was saying that the in degree means how many edges are coming into that particular vertex. And the out degree means how many vertices are moving out of it. All right, so we are given a graph here. And then we are asked to identify or what are the out degree of the vertices. Okay, let's speak about the in degree first. So we are given this graph and then asked to find the in degree of the vertices in the graph. And if you ask such a question, you have to consider all the vertices in the graph and write down all their in degree vertices alongside them. And mostly we write the in degree with this symbol here. So we have the degree and then we have the minus at the top. And then we bring the specific vertex that we are considering at a particular time. So at this point, we have the in degree for vertex A to be 2. Right? And then we have the in degree for vertex B to also be 2. And similarly, we have the in degree for vertex 3 to be, vertex C to be 3. So let's consider the vertex A and try to see if it's actually 2. This is the vertex A we are considering, and look at the arrows. How many of them are actually moving into A? This is moving out of A, so we are not going to consider that. This is also moving out of A, so we won't consider it. Similarly, this is also moving out of A to C. It's not going to be considered. However, from E, we have one of them which is moving towards A. So we consider that one as one of the degrees. Now also on the same A, we have a loop over there. This particular one here. That also accounts for one of the degrees. And so the number of degrees that are moving into the vertex A are now 2, which is from E to A and then from A to A itself. That is why we have 2 over here. And if you look at B also, we are going to find the same thing here. This is B. And we have this one moving to it and this one also moving to it. So that makes it the in degree to be 2. So if we are talking about directed graphs, then we have the in degree and then the out degree. Undirected graph, then we have just degree of the vertices and we are good to go. And now the out degree happens to be the number of edges that are moving out of A. Out of F, given vertex. And so we count them and then we equate it to the specific vertex we are considering. So if we are to consider this one here, the out degree of vertex A is giving us 4, that of B is 1, that of C is 2, and then we have F to be 0 because there's none of them moving out of F. And we can confirm from this one here, there's no degree that is moving out of F. neither do we have one that is moving into F. So both scenarios, if you are writing the out degree, it's going to be 0, and then the in degree will be 0 as well. Please, are we clear with the in degree and then the out? All right,
Yes, sir.
considering
Thank you, sir. Like with the A, I can see the out degree to be 3, but the answer is saying 4. So I'm wondering a little bit.
you have the
For
out
if
degree
you
to
can
be.
check and see. I see to be
I didn't
3
get a question. Can you the out degree for which vertex, please?
for A. For A.
Okay, for A. All right, let's try to consider and see if it's actually
Okay.
4 or 3. So we have this one of them, right? One of the out degrees. This one here. And then we have this as another one as well. Right? And then we have this as another one as well. That is 3. And then we have this loop also as one of them. If you could
Please,
remember
come
when
on.
we were talking about undirected, we said that a loop contributes to 2.
Yes,
Yes,
please.
please.
All right, so the reason why the out degree for the vertex A is 4 is that we have a loop on it. And if you could remember, when we're doing the undirected graph, we said that if you have any loop on a vertex, it contributes to 2 degree of vertices. Because since there is no direction, it could be an in degree and then also an out degree. So that makes it contributing to 2 of the vertices for the degree of vertex. However, when it is a directed graph, you separate the in degree from the out degree to get 2 of them. So if you are writing for the in degree, then we add the in degree to it. If you are writing for the out degree, we add the out degree to it. Because it's a loop and it can come back to A and then move out of A as well. So it's moving out becomes the out degree, and it coming to it is the in degree. That is why we have the out degree for vertex A to be 4, but not 3. Please, is it clear for all of us?
Yes, sir.
Is it clear for everybody? Have another loop as well. So to count the number of out degree, then this one is moving out of it. That is one of them. And then plus the loop itself, the loop can move in and then move out at the same time. So it's moving out contribute to one of the out degree vertices, and then it's moving in contribute to one of the in degree vertices. So that makes this particular out degree of C to be 2, because we have C to D, C to B, and then C to itself. Please, are we clear? All right, so let's move on to another theory here, which says that given a graph V of G with directed edges, we could see that the number of edges is equal to the sum of the in degree and the same as the sum of the out degree. So if you have, let's use this graph for instance and try to understand. let's consider which one is the simplest one. Okay, so let's consider the vertex B and try to understand what we are talking about from here. So note that we said the absolute value of the edges or the total number of edges is equal to the sum of the degree of vertices and then also the sum of the out degree of the vertex. So in degree and then out degree will give you the number of edges for that particular vertex. So considering this one, for instance, if we want to find the number of edges that are connected to D, then we could use the out degree to determine those ones. That is what we are basically talking about. So if you take the out degree for D, which is 2, the number of edges that are connected to it are just 2. So that is what we have. The edges is equal to the sum of the out degree, and it's also the same as the sum of the in degree. Right, and this is the proof for, this is the theoretical proof or the text to prove that. So the first sum counts the number of outgoing degree over all vertices. That is what we're talking about here. And the second counts the number of incoming. So that is, and the sum of this equal to the number of edges that we have in the graph. Please, are we clear? All right, so let's move on to what we call a complete graph. And I believe we understood complete graph from algorithm, but a complete graph on n vertices denoted by k of n is the simplest graph that contains exactly one edge between each pair of distinct vertices. It contains exactly one edge between each pair of distinct vertices. So let's consider this particular K1, for instance, which has only one vertex. This can be said to be a complete graph. This can be said to be a complete graph because of this statement we just read here. And also, this can also be said to be a complete graph. However, this one has only one vertex, and this one has two vertices. So if it has more than one vertices, then
Say your screen, oh. Your screen. Your screen is not showing.
I think it should be from
Your network is bad.
yeah, but if it was the network, I don't think you could have heard me. You wouldn't have been able to hear me. Let me reshare the screen and see.
Okay, fine now.
Is it clear now? Okay, all right. So as I was saying, the complete graph having n vertices, and then if it's denoted by k of n is the simple graph that contains exactly one edge between each pair of distinct vertices. So if you have a graph that contains exactly one edge between each pair of the vertices that are available in the graph, then we could see that that is an example of a complete graph. And now to make it simple for us in layman terms, if you have a graph and all the vertices can be reached directly from one of them, then we could say that's a complete graph. So assuming this is to model a simple network, that is vertex. Let's assume this one here. This one here and this one here are A, B, C. So if you stand at B, you could be able to move from B to C and also B to A without passing through any of the other vertices in the graph. So if you have such scenario, then we could say that this is a complete graph. You stand at one vertex, you move directly to any other vertex that is in the graph, then that becomes a complete graph. So let's take the K4 for instance. That is a graph with 4 vertices, for instance. And we say the first vertex should be, this one should be C. If it is a complete graph, then you can move from C. If it is a complete graph, we can move from C to, let's say, A directly. And the same way, we can move from C to D directly, and then from C to E directly without going through any of the other vertices that we have. And that becomes a complete graph. So if you start at vertex A, you can move to C, you can move to E, you can move to D. That makes it a complete graph. You don't need to go through any of the other vertices to get access to the others. That becomes a complete graph. Please, are we clear?
Yes, sir.
All right, let's also look at a circle. So for a circle C of n, where n is greater than or equal to of n vertices. Ambassador Dennis.
Thank you, sir. Please, at what point a graph become incomplete?
That is if you can't move from you when you stand at one vertices, you can't move to any of the vertices directly, then it's not a complete graph. So assuming that we add another vertex to this and then probably name it as F. There's no way to move from C to F without passing through any of the other vertices. That makes it not a complete graph.
You made some demonstration. I did not see.
So let me clean and then do it again. So we are considering the K4, the graph with vertices 4, right? And this one could be an incomplete graph if we extend from here and add another vertex like maybe F. So what it means is that if you want to move from one of the vertices, you need to visit some vertex before you get to F. That makes it an incomplete graph.
Okay.
Yeah.
Well understood. Thank you.
Okay. All right, so let's talk about a circle C subscript n for n which is greater than or equal to 3, consists of n vertices v1, v2 up to vn, and edges v1, v2, v2, v3, vn minus 1, vn, vn, and then v1. That's if you have this particular scenario, then we could see that it is a circle. And basically what we mean is that And basically what we mean is that if you are given a graph and we want to determine if it is a complete graph, I mean it's a circle, then the number of vertices, which is n, might be greater than or equal to 3. Then we could say that this is a circle. Because if you have the vertices less than 3, then it doesn't qualify it cannot be considered as a circle. So the number of vertices should be equal to 3 or greater than 3. And so to start that instant, we can have C3, C4, C5, and C6. And this is how it looks like. So for C3, we have a complete graph for it. And then C4 is also complete, but the rest are not complete because there's no connection from here to here, this, and then this as well. So basically, to get a circle, the number of vertices must be equal to 3 or more than 3 to be able to model a graph into a circle form. Please, are we clear? I don't know if someone can actually connect two vertices to get a circle. Maybe the person can help us understand that. All right, so let's move on to another type of graph, which is called a bipartite graph. I don't know why it's not showing again. All right, so a simple graph G is called bipartite if V can be partitioned into two disjoint subsets V1 and V2, such that every edge connects a vertex in V1 and a vertex in V2. Or in other words, there are no edges which connect two vertices in V1 or V2. So with a bipartite graph, it basically means that we're able to separate or partition the graph into two disjointed subsets. And we can name them as V1 and then V2. And then if we are able to do the disjoint subsets, the condition is that every edge connects a vertex in V1 and V2 as well. So every edge connects a vertex in V1 and vertex in V2. And then in other words, there are no edges which connect two vertices in V1 or V2. So that becomes a bipartite graph. And we have to know that an equivalent definition of a bipartite graph is a graph where it is possible to color the vertices red or blue so that no two adjacent vertices are the same. I mean, have the same colors. So this is an situation that we have here. So if we are able to color the vertices red or blue so that no two adjacent vertices are the same, then we could say that that particular graph can be a bipartite graph. I think you could check your network, it's showing. Ambonsa Dennis.
I think it's the previous one that I read. Okay.
Okay.
Thank you.
Henry, your hand is up.
Yes, sir, please. Sir, please, I'll be happy if you can please explain the bipartite graphs again for me.
Oh, okay.
I didn't get the division very well.
All right. So what I'm saying is that for a bipartite graph, let's say G, it can only be considered or called a bipartite if V can be partitioned into two disjoint subsets, that is V1 and V2. And then in that scenario, every edge connects a vertex in V1 and a vertex in V2. And then to further add up, we can say that there are no edges which connect two vertices in V1 and or V2. So the simple way to determine if a particular graph could be a bipartite graph is about graph coloration. That is, if it is possible to color the vertices red or blue so that no two adjacent vertices are the same color, then we could say that that graph has the potential to be a bipartite graph. That is, we partition them into disjointed subset V1 and then V2. I don't know if it's clear now.
Still not clear, sir.
All right, so you let's move on. After the class. I think we have graph partition somewhere. So when we get there, and then you don't forget it, I'll come back and explain. Right.
Okay, sir.
All right. All right, so let's see some examples. Ambassador Dennis.
Sir, with the bipartite graph now, like the partition that we are talking about, is it not like separating the graph into two, or making the graph like making them separate, like maybe A and B, whereby they are all formed in one this thing?
Yeah, so yes, we have an example here that I want to show, but it's not loading on your screen yet. When it comes, you see how it works. So let's work with an example and see how you understand it here.
All right. Thank you.
Okay. Let me reshare the screen and see. It's delaying. Yeah. Please, can you see the screen?
Yes, please.
All right. So, sorry. So now we have this particular graph here, and we are asked to show if it is bipartite or not. Right. And one of the easiest way is the coloration, but then we don't have the coloration. So let's do the partition to see how it works. So we can partition the vertices sets, as we said earlier, V and V2. And then after that, we try to connect them and see how it works. So we partition the vertices set into V1, which is V1, V3, and then V5. And then V2, we have V2, V4, and then V6. So that every edge of C6 connects a vertex in V1 and then V2. So if we partition it this way, this becomes our V1 and this becomes our V2. Right? So now if every vertex in V1 connect to a vertex in V2, in that scenario, we could say that the graph is a bipartite graph. So we have V1 that connects to V2 here. Let me clean the. So we have V1 that connects to V2 over here. Similarly, we have V3 that connects to V4. We have V5 that connects to V6, and the same V5 connect to V4. So if you have that scenario, then we could say that that is an example. A graph given is an example of a bipartite graph. Basically, and in the partitioning of the V1 and V2, you have to make sure they are even. You have to make sure they are even. We have 6 vertices over here. That is why we have C6. So we have 6 vertices here, 1, 2, 3, 4, 5, 6. And in a partition process, we partition them in a way that each V1 has 3 vertices and the other has also 3 vertices. So if V1 connects to V2 or every edge of the graph given connect to a vertex in V1 and V2, then we could say that that is a bipartite graph. Please, are we clear? And a normal circumstance, you give vertex name to the particular graph over here. All right, so as I was saying earlier, we have to give numbers to the vertices so that you can separate them quite properly. So we have V1, V2, V3, V4, V5, V6. So we could just number them over here to make it easy for us to identify the graph. So this could be V1, this could be V2, and then in the separation process, we have V1, V2, V3, V4, V5, and then V6. And if every edge of the graph that is being given to us connect to a vertex in either of the partitions, then we could say that this is a bipartite graph. Please, are we clear? Ambassador Dennis.
Thank you, sir. In a situation whereby the C is 5, how is it going to be done?
It can be a bipartite.
Okay, so which means that it deals with even numbers.
Yes, and it doesn't necessarily mean that the even number is a constant for it to be a bipartite. No, it has to satisfy the conditions we specified earlier. That every edge of the graph connect to a vertex in the V1, V2 partitions.
And so I was thinking like, because of the distribution going to be evenly, automatically taking even number will be possible.
No, that won't be possible.
Yeah.
That won't be possible, yeah.
But it will link to each other like back and forth. As compared to
I didn't get
the
you.
odd. I know the even number, this one is linking like maybe V1, V2. Like when we divide it into 2, maybe having the V1 and having the V2, like distributing it evenly possible.
The network just went off when you're about to end, so can you just repeat yourself?
I was saying that
okay,
since the partition is like taking two various aspects. Maybe we have divided this one, the C6, we have divided into two, which we have the V1 taking maybe V1, V2, V3, and this one aspect taking the other three. So distributing
Yeah.
it evenly to be possible. I was thinking maybe for the odd aspect is out, but taking to be even numbers, I think
Okay.
it will be possible.
All right. So you remember earlier we spoke about loops, right?
Yeah.
And the issue is that for each of the group, none of the vertices should connect to themselves in the same group. So imagine we have a loop over here.
Oh, okay. If if that be so, which means that the loops will count like twice.
And then it will connect the same vertex, which is not what you're supposed to do. Yeah.
Okay, I get it. So I shouldn't rest my case on the even numbers. Sure. All right.
And even with that, if we have another edge connecting here and then here, there's a possibility that V1 and V3 can be connected in the same group. And in that instance, you cannot call it a bipartite. Please, are we clear?
Oh, okay. So it shouldn't be like cross this thing. Like I don't know how to put it.
Okay, so we can say that we can make it cross-pollination, but not self-pollination in that sense. Right? If the connection happen within the same group, that is not acceptable. It won't be a bipartite. But if it's connection between one group and then the other group, then that is okay.
Sure.
Please, are we clear? Henry, are you okay now?
So for me, there,
I'm still figuring it out.
yeah, for me, there, I'm totally confused by bipartite. I don't know.
Okay,
If you can.
let's understand it
Oh, right.
let's understand it from here. When we talk about bipartite, it means that we can divide the various vertices of the graph into two, right? To two separate groups. And then we can label them as the group as one of the group to be V1 and the other to be V2. And in V1, we have vertices in it. V2, we have vertices in it. And what makes the graph bipartite is that for every group vertices we have in each of the group, it should connect to the other group. So considering this graph, for instance, here we have C6, which has vertices, six vertices. And what we have to do now is divide the vertices into two. That is going to be the partition we spoke about earlier. So we have V1 here, we have V3, and then we have V5 in the first group. Now in the second group, we have V2, we have V4, and then we have V6, right? So now what we have to do now is connect each of the vertices in V1 to V2. If there is any instance where a vertex in V1 connects to a vertex in V1, then the graph is not a bipartite. Please, are we clear? So in this scenario, let me just number here to be 1, 2, 3, 4, 5, and then 6 here. So now if you take vertex 1, do you have a connection from vertex 1 to vertex 2? Yes, so we connect it here. Do we have from vertex 3 to vertex 2? Yes, we have, so it's here, right? Do we have vertex 3 to vertex 1? I mean, yes, do we have vertex 3 to vertex 1? if that is possible, then the graph is not bipartite because we cannot connect the same vertices in the same group. Please, how we are following. Now moving on to vertex 3 can connect to vertex 2. That's true. Vertex 4 connect to vertex 3, connect to vertex 4. That is also true. And then vertex 3 cannot connect to vertex 5. And that is true from the graph, not what we are seeing as the solution. From the graph, vertex 3 is not connected to vertex 5. So we move on. And now when we are done, that's vertex 3 connect to vertex 6. From the graph, that is not the case. And move on to the next vertex, which is vertex 5. Vertex 5 does it connect to vertex 2? That is not true. Does it connect to vertex 3? That is not true. Does it connect to vertex 6? That is true. So we have this one here. So this one makes it a bipartite because none of these groups connect to themselves here. The same way applies to the group in V2. But then if we have a connection from, let's say, this is 3, so 3 to 5, then it means that we have to connect 3 to 5 here. And in that instance, that is not a bipartite because for every group, there shouldn't be a connection between the vertices themselves, but then it should go outside. Please, are we clear?
Yes, sir. So, sir, please,
All right.
If I got you right, if given such a question, you can, after giving them the numbers, you can put all the evens at one side, put all the odds at one side, and check to see if they connect.
Yes. Exactly. So you can group the vertices as even vertices and odd vertices, and based on the number that you give to them.
Okay.
Yeah. And then you try to do the connection.
Thank you, sir.
You're welcome. Please, any other question?
Sir, so what it means is that when you take, let's say, V, per the labeling that you did, V1, V2, V3. When you take V2, V2 can only connect to V1 and V3.
Yes, but you have to consider that from the graph, not your mind. Because you are based on the graph to determine if the graph is a bipartite or not.
Yeah, so in this case,
graph,
in exams, there are two diagrams that we are seeing. The one at the top and the one at the down. They will give you the top one and you will draw the down one, or they are going to give you which one are they going to give to you? The down one for you to draw the top one, or top one for you to draw the down one, or both?
The one in the red circle is the question. Show that C6 is bipartite. And then this one below, the solution is the answer. Yeah.
Okay.
So this
good.
Solution is the answer.
Yes. So per the diagram I'm seeing it to be that if you have a V1 can only connect to V2 and V6. Because when you label it, when you label it, yes, that means each vertex that you pick, it's adjacent. It's adjacent vertex.
Yes.
It's what we are talking about here. Okay.
Yeah.
All right. I get it.
Okay. All right, and then we have another one here. So who can help us understand this one? Show that C3 is not bipartite. Ampana Kwaku.
Please, sir, I have a question to ask. On
as
the vectors, on the vectors, I want to know how will you identify that this one is V1?
So that is why earlier said we should have numbered them. Before you could know this is V1, this is V2, this is V3.
So please, can you start from any place at all and then number from starting from V1 from the graph?
Yeah, so ideally, if you are not given, I mean, let's be systematic. You can't start from anywhere like 1, 2, 3. It should be, I don't know whether clockwise or anti-clockwise. So this is 1, this is 2, this is 3, this is 3, this is 4, this is 5, and then 6 in that order. But then it doesn't matter. Anyhow you number it, if it is a bipartite, you'll be able to know, regardless of the position of the numbering. All right. So who will help us understand this one here? Show that C3 is not bipartite. All right, so this is what we have here. Henry, please don't read the solution for me. Just tell me what's on your mind.
I'm not going to read the solution. I'm not going to read the solution.
Okay, okay. All right.
If I remember very well, I think someone asked a question and you said that once it's an odd number, that means it doesn't qualify to be a bipartite graph.
Yeah.
I stand for correction. So if that is the case, then this is an odd number, and I think it doesn't qualify. That's the first thing that comes to mind.
All right, that's true. That's very true. All right, and even if we divide the vertices, I'm reading from the answer of the C3 into 2 non-empty sets. Definitely one of the 2 vertices will contain, let me say, will have a connection to itself in the same group. So let me number this so that we try to understand it. So we have 1 here, we have 2, and then we have 3. And now let's try to understand. So we have V1 here, which is 1, and let's say 3, right? And then we have also only 2 inside V2. We have only 2 here. So now from the graph, I'm reading from the graph. Please, the drawing is not to scale. Just follow up. So from 1 to 2, there's a connection. So that's we have to connect the vertices from 1 to 2, from this group to this group. That is correct. Now from 3 to 1 is possible. 3 to 2 is possible. So 3 to 2. We have a connection which is 3 to 1. But 1 and 3, vertices 1 and 3 are in the same group. So if that situation occurs, then the graph is not bipartite. Please, are we clear? That is what we are saying here, that if we divide the vertex set of C3 into 2 non-empty sets, one of the 2 must contain 2 vertices. That is what we have for V1. Therefore, the 2 vertices in the same partition are connected. That's what we just did, 3 and 1. And C3 is not bipartite. So in an example where you are giving such question in an exam, when you number them and you are trying to provide an explanation like we have, I would prefer you to use the vertices that will connect themselves in the same group to make it much more easier for us to follow. So obviously, if it is an odd vertex, then you can't get a bipartite from it. But if it is even, that is when you have to move further, divide them, and then try to do the connection of the vertices from one group to the other. So you can determine if it is bipartite or not. Please, are we clear?
So my question is based on the first example, the solution. We use mapping over there, and then the second one, that one too is description. I want to know, can you also answer the first question? That is this one, like in the form of description form without using that mapping over there.
You know, in most cases, graphs and drawings are easy to follow compared to so much writing. So if you just see that the graph has even vertices, please just divide it for us to see how it works. And then I did in either cases, if it's a 3 vertices or 6 vertices, whether odd vertices or even vertices, you can draw it and then you show the connection to from one group to the other or within the same group. Even without explanation, we can understand what you're doing. In most cases, we don't really emphasize or focus on the answer, though the answer also has marks, but the approach can help us understand that here you have the idea, but probably something happened. So when you draw, separating them into the various V1, V2 groups give us the idea that you understand what you're doing. Right, so there's plenty text there. It won't really help us much.
Sir, right. Please. So on this, will you redraw the graph in your solution and number them according to their vectors before you come and do the mapping, or you not draw the graph again? And you not draw the graph again. You just do your vectors.
So when we are giving out the questions and the timing allocated to them, we don't include you repeating the question for us. That is drawing the already given graph already. We have sample. So go straight and give us the solution. That is all. So probably can give a preamble like and numbering the graphs. I want to hear you. You said something.
Yeah, I want to know, like, the question one, the vectors were not numbered. The graph over there, it was not numbered. Yeah, this one. Yes. So in case I'm going to represent mine, how will you know that this? If I start describing this one, V1 is V1 map to V2, and then the rest. How will you know that my V1 on the graph is located at somewhere this place and this place, if I didn't draw it?
Yeah. So I was saying that wherever you start numbering from, you're going to get the same, whether it's by pie chart or not. And so to make things easy for us, you do the partition based on the odd and even numbers. So if you look at this here, for instance, the V1 contains odd vertices and V2 contains even vertices. So regardless of where you start numbering, you can get where you're coming from. But if you mix them up, you have even numbers in V1, even numbers in V2. That might be difficult for us to follow. So to be systematic, one of them contains odd vertices and the other contains even vertices based on your numbering. Yeah. So you can give a preamble like assuming the vertices are numbered V1, V2, V3, V4, and then you proceed with the solution. That's all. So drawing will just waste your time. We have the question already. All right, so let's talk about some use cases of bipartite graph and some sort of matching. So you can use bipartite graphs to model applications that involves matching the element of one set to element in another. And this is very important for job assignments. So the vertical vertices represent the jobs and the employees, and edges links employees with these jobs they have been trained to do or assigned. And one of the common goal is to match jobs to employees so that the most jobs are done. And so you have the employees at the top here, and you have the various jobs that are over here. So the main objective is that we match jobs to employees so that the most jobs could be done. Right, so if you take Alvarez, for instance, Alvarez is matched to testing of maybe if it's a software. And then we have Davies is also matched to requirement analysis or requirement gathering. And Bekowitz is also assigned to the implementation, and Cheng is assigned to the architectural design. So this is how we can sort of match job assignment to individuals using the bipartite graph. Please, are we clear? And you could see that none of the individuals are matched to either, that they are not combined to probably perform a specific task. Each person from a group has an activity that he or she is supposed to perform. So that is how one of the bipartite graph can be used in job assignment. All right, and then we have complete. I don't know why the screen is not showing. We have complete bipartite graph as well. All right, so let's talk about the subgraphs. Please, can you see the screen?
No, please.
I don't know. Yes. Let me reshare again. All right, so with the bipartite graph, we have also complete bipartite graph. And what all these plenty mathematical definition is talking about is that if you divide the graph into the various groups that we have, the V1 and then the V2, it means that each vertices from one set of the group is connected to every vertex in the other set of the group. So if you have, for instance, what we saw earlier here, the screen. Please, can you see the screen?
No.
I think you have to check your network. So when we talk about,
I can see a screen.
It's not showing.
Just a minute. Is it showing now?
Yes, please.
Right, so there are plenty. Right, so the plenty definition you're having here is that for every complete bipartite graph, group one should, I mean, the vertices in group one should exactly or should have a connection to that of the vertices in group two. So in every group, every vertex from one set is connected to every vertex in the other set. So you have V1 connecting to maybe B2 connecting to B vertices in the that way. So let me see it and get there. Okay, so for instance, V1 connects to V2, V4, and V6. Similarly, V2 connects to V2, V4, and then we could say that the graph that is given to us is a complete bipartite graph. Please, are we clear? So that is what a complete bipartite graph basically means. And we are giving some examples here to determine if these ones can be complete bipartite graph, or which of them is a complete bipartite graph. Can someone just guess for us? We have K2 and 3, and then K33, K26, K35. Anywhere to guess for us? Anybody? Please, can you hear me?
Yes, we can hear you. But the labeling in the diagrams are not clear.
I want to try, but it seems the screen is off. I don't know whether it's my end or the whole.
Is the screen showing now?
Yes, sir.
Yes,
sir. It's showing.
As a going try for us, I'm considering this.
I think I'll go for the complete one. I'll go for which one? Is it K? The second one. The second one.
K33. This one here.
Yes, please. I'll
All right,
for that
so
one.
I'll just recommend that you go and try it out and see. But then when you're giving, I mean, a lot of graphs to determine which one is complete bipartite, you have to consider which one doesn't qualify to be bipartite before you move on. Right.
Oh,
so we
okay.
have this one here, for instance. This probably wouldn't be a bipartite because of the odd vertices.
Oh, exactly.
And then you move on to the other. So if they have even, that is when you have to now move on and check if every vertex in one group connect to exact another vertex or all the vertices in the other group, and then you could say that it is complete and bipartite as well. Now let's look at subgraph. Okay. So a subgraph of a graph is a graph WF where W contains V and V also contains F also contains E. And then a subgraph H of G is a proper subgraph of G if H is not equal to G. So given this particular graph P5, one of its subgraph is given here. So subgraph basically means we getting a graph from a graph. Henry.
Subgraph cannot be seen, please.
Let me restart my machine and join again. I don't know what's happening right now. Probably it will work this time or that time. If it was a network, you would have been able to hear me. All right, so let's continue and see if the screen will be stable for the rest of our time left. So we're talking about subgraphs and
Sir, please, before the subgraphs, can you go back? Before subgraphs, I don't know if it's possible if you can throw a little light, just 1 minute on this, so that I'm pleading if you can
just complete
for the network. Yes, the complete this network.
Oh, okay. All right, so Lindsay, what I was saying, consider a graph as complete bipartite graph. It basically means that for each of the groups that we have divided the graphs into, every vertex in one group should connect to another vertex in the other group. And this is an example that we have. So if we group this graph into V1 and V2, and we have vertices V1, V3, V5 in group 1 or group V1, and then we have vertices V2, V4, and V6 in group 2, then it means that every vertex in V1 should be connected to every vertex in V2. Then we can see that that graph given is a complete and bipartite graph. So in this scenario, for instance, this is not a complete bipartite graph because some of the vertices are not connected to some other vertices in the other group. If we consider V1, for instance, it is not connected to V4. So you cannot consider that as a complete bipartite graph. The same way, V3 is not connected to V6. So we can't say this graph is a complete bipartite graph. It's always clear.
Yeah, but sir, if I understand you clearly, you are saying that it is a complete bipartite graph. If after dividing them into two, V1 connects all the vertices in V1 connect to all vertices in V2, then we call it a complete. Is that what? I don't know. That is what.
I didn't hear what you said earlier.
No, we are talking about complete bipartite graph, and we are saying that it is a complete bipartite graph if all, for example, with this particular one displayed, if all vertices in V1 are connected to all vertices in V2 such that there are no vertices left behind, then it is a complete bipartite graph.
Yeah.
So, and you're also saying that this one displayed right now on the screen is not. I don't know whether I didn't hear you clearly, but you are saying that this one is not a complete.
Yeah, it's not complete. Yeah.
Why? I don't understand why.
Because we have vertex V1 that is not connected to V4. Just look at the graph, you see it over there.
Hello.
Where is it, Papa?
Yeah, man.
I can see.
Solution. V1 is not connected to V4.
The screen is off.
Mm-hmm.
Okay, it's back on.
You check. V is saying V. Oh, it's gone. Well, Lindsay.
What I'm trying to say is that you are not getting me. What I'm trying to say is that all vertices in V1 have a connection in V2. That is what he is trying to make us know, because all of them are at least connected to a vertex in V2. So that makes it a complete bipartite graph. That is the explanation he gave. And per the diagram, all V1s are connected to V2. Everybody has a connection. There's no one left behind.
But you can't be on one that connects to all. At
No,
the time, you can't be on one.
No, not one connecting to all. One connecting to at least one in the other group. That makes it complete. Then
No.
Yes, unless he
No,
comes
then
again. Then maybe unless he comes again.
Yes, that's what he's saying. Yes, that's what he's saying.
Okay, so if that is what he's saying there, then per the diagram displayed, at least one a vertex in V1 is connected to a vertex in V2. Nobody is left behind.
Valencia, let me come in here.
What? Yeah, one is left behind. You cannot see it. That V1 is not connected to all of them.
Valencia, hello. Please, can you hear me?
Yes, sir.
Yes,
Please,
sir.
can you hear?
Yes, sir.
All right. So this is the scenario, right? We learned earlier that for a complete graph, you should be able to stand at one of the vertices and visit each of the vertices on the graph directly. You don't need to pass through one other vertex before you get to where you are going. So the same scenario here, if we are talking about complete bipartite graph, it literally means that if we divide the various vertices into V1 and V2, for every vertex V1 in the group V1 should have a connection in every vertex in V2. So with the example on the screen, we have V1 that is not connected to V4. Please be clear. And we have that is not connected to V6. Similarly, V5 is not connected to V2. That makes this one not a complete bipartite graph. And I didn't say at least one in the other group. If you have 6 vertices in V1, all the 6 vertices must connect to all the other vertices in V2. Then that becomes a complete bipartite graph. Please be clear. Valencia.
Okay, sir, clear. So yes, sir, clear. So let's go to the complete graph. The one you showed.
Are you
the complete bipartite graph? Let's go to.
Okay.
Yeah, this is okay. So okay, let's go to the complete.
This is complete bipartite graph here.
So now let's pick it up from this with this. How is this explanation like?
All right, so let's take the first one, K2, and then 5, right? K2 3. So we have let's label. We are taking the first graph. So this is one vertex 1, vertex 2, vertex 3, vertex 4, and then 5, right? So now if you divide this one into group V1 and V2, we are going to get 1, 3, and then 5. And then we are going to get only 2 and 4. Please, I hope we are following. This is 3, and then the last one is 5. I hope we are following. So now we have a connection from 1 to 2. Is that the case? Do we have direct connection from 1 to 2? That is not the case.
No,
right?
no.
All right. So
No.
do we also have connection from 3 to 2? Yes, we do have. So we connect here. Now we go to Do you have connection from 3 to 4? That is not the case. So
No.
you move on to the fifth and the other vertex, which is 5. Do you have connection from 5 to 4?
No.
That is a no. Do you have connection from 5 to 1? We have a connection from 5 to 1. So obviously this is even not qualified to be a bipartite. So we cannot even proceed to compare to check if it is complete bipartite or not, because we have 1 and 5 in the same group, and then they are connecting to each other. So this first one doesn't qualify to be bipartite. So we just leave it. All right. Oh, we can't hear you, Obakari. All right, so let's wait for him to come, but then we move on. So the first one doesn't qualify to be bipartite, not to even talk of moving on to check if it is complete or not. Now let's look at the second one over here. We don't have much time, but let's try to understand it. So we have 1, we have 2, we have 3, we have 4, we have 5, and then we have 6, right? So in dividing, then we have 1, 3, and then 5. And then also we have 2, 4, and then 6.
The naming,
hello?
The labeling of the vertices. Is it done in a systematic way, or you can do it haphazardly? Or
yeah, so I said earlier that regardless of how you do it, the separation should be odd vertices against even vertices. That is why 1, 2, 3, 4, 5, 6, and then we have the V1 to be 1, 3, 5, and the V2 to be 2, 4, 6.
All right.
Even vertices at one end, odd vertices at the other. So now, do we have a connection from 1 to 2 based on the second graph? That is a no. Right?
No.
So do you have 1 to 4? That is true. So you have 1 to 4 here.
Yes.
Do you have 3 to 2? That is no. Do you have 3 to 4? That is also no. Or that is yes. We have 3 to 4.
Yes, we have 3 to 4.
Yeah. Do you have 3 to 6? We have 3 to 6. Now we move on to the fifth one. Do you have 5 to 2?
Yes.
Yes, we have 5 to 2. Do you have 5 to 4?
No.
We don't have 5 to 4. Do you have 5 to 5? That is a no. But we have 5 to 1.
Okay.
Yes.
Okay.
Which means this even does not qualify to be a bipartite graph.
Okay.
So we move on to, so we are going to do this until we make sure that each of the divisions
please, my question is, the moment, the moment you got to know that one vector is not connected to another vector, can you conclude from that particular place that the graph is not complete graph?
Just move on. No, you don't have to waste time. Just state why it's not a complete graph, and then you move on. Yeah. So now 1 and 2 doesn't even qualify to be bipartite. Not talk of they being complete. Now you can do the same for 3 and then 4. And you can determine if it is bipartite and then also if it is complete. I hope we can do that. We don't have much time because of the network issues. Abubakari, your hand is up again.
Good morning, sir. Please, sir.
Good morning.
I am a bit confused here because when you look at the especially the first two graphs, I don't know if it is mandatory that we number from, let's say, clockwise, or otherwise, if we are to number, let's say, from top to down, I think all the graphs would have been a complete bipartite. So I don't know, in the case of exams, is it a mandatory to go clockwise? Otherwise, when we look at the first graph, if we were numbering from the first one, the bottom to
please walk us through. Let's number them so that you tell us if it is bipartite or not. So where do we start? Do we start from here?
Yeah, so let's take the first graph, for example.
Yeah.
The top.
So do we start from
the
here?
First up to the top, please.
Here, okay. So this is one, right?
Yes. Then the bottom two.
Okay. Two.
Then the next top one.
Three. This is three. Here, three.
Yes. Then the bottom mid. Four.
Okay.
Then 5 to the last one.
And then this is 5.
Yes, please.
All right, so help us divide this number. So V1 will be what?
So our even numbers, if we should group them to our even and odd numbers. We
have one.
The odd numbers, which 3 and
1, 3, 5.
Yes.
I want to let you move further. Look at. I want to let you move further. So we have 1 and 5 in the same group. Look at this. Look at this connection here.
Exactly.
Okay.
So either way, you number them, but then you have to be consistent in the explanation. If you miss the explanation, then you wouldn't get the concept or how you want to present it. So regardless of how you number them, you'll still be able to tell if it is bipartite or not bipartite, and then you further move on to talk about the completeness.
Okay, thank you so much.
Clear? Okay.
Yes.
All right. All right. So please, the other two, just go and try your hands on them. All right. So we're talking about subgraph, and when we talk about subgraph, it's just a component of a graph that we have extracted from a given graph. So given this particular K5 graph, one of the subgraph that we can get is what we have here. This one here. So this is one of the subgraph that we can extract from this particular given graph here. So if we are able to get a component of a graph from a given graph, then we can talk about that component as a subgraph. And mind you, you have to make sure that all the vertices are included and all the edges are also included before we can say that this is a subgraph. So if you are to trace this particular subgraph from the given subgraph and from the given or the main graph, this is what it might look like. So we have B to C. So we have this over here, B to C, which is the edge. Then we have B to A, which is also this one here. We have A to C, which is this one over here. And then finally we have E to D or D to E, which is this. And then finally A to this one. So this is one of the subgraph that we have extracted from this whole given graph. The same way you can take this as a subgraph as well. So we have this E2. Let me change the color here. So we have E to D, D to C, and then C to A. So this can also be another graph as well. And mind you, since we said earlier that a graph can have just a vertex, you could say that all of these A, B, C, D, E can also be subgraph from this main graph that's given to us as well. So that is how the definition of a subgraph basically looks like. All right, and then this is also another definition for subgraph. So if G, which is a graph given as VE, vertices and edges, be a simple graph. The subgraph can be induced by a subset W of vertices set V, and then it can be termed as a graph WF, where the edges are, the edge sets F contains an edge in E, if and only if both endpoints are in W. So basically what we are talking about here is that if we deduce a subgraph from a given graph, we have to make sure that all the edges are in the subgraph that we got from the main graph that was given to us. So assuming this is our graph, then we have all of these edges or vertices that are gotten from this particular main graph that is being given to us. And then you cannot move outside and add your own graph. If you add your own graph, then you are constructing a new graph, but not a subgraph from the graph that's been given to you. All right, so since we have subgraph, we can have union of graph as well. And then as we all know, in union, it literally means that we have two subgraphs and then we are asked to add them all together to make it a complete and single graph. Right, so this is the definition. So the union of two simple graphs, G of 1 is equal to V1 and E1, that is edges 1 and then vertex 1, and then the G2 will be vertex 2, vertex. And then it should have the vertex set VU union V, V2, and edge set EU, E2. That is, you add you take the, how do you call it, the union of the edges and the union of the vertices. And in that sense, the graph is going to be G1 union G2. So this is an example that's been given to us. So we are given this graph G1, and also we are given this graph G2. So the union of these graphs is going to be this one over here. Right. So this is more like the main graph given to us, and these are sub-component or subgraph from it. And we are asked to make them all together. Please, are we clear? Henry.
Yes, sir. So please, looking at the diagram A and B, I can see that A, as you said, put together, the two things put together, or the two graphs put together has given us B. But looking at the naming, we're looking at the J1, we have A, B, C. And then looking at J2, we have A, B, C. Yeah. Does that mean that in exam or something like that, we're going to be giving the naming of the various vertices?
Yes, so each graph will have the various vertices in them.
As in, are they going to be named?
So you mean they are going to be named like A, B, C?
Yes.
Yes. So yes, they should be named. They should be named, because if these ones have different names, then it won't result in this graph we have. It will give us a different set of graph altogether. But because this one have different names, that's why I'm merging these to this one to get this particular edge here.
Okay, sir.
Right. Yeah. So the graph vertices are going to be named for you. Abu Akari. Abu Akari, your hand is up.
Sir, I'm saying that, so with union graph, you have two different graphs that somehow has the same names of their vertices, like the ABC Henry talked about. You see in graph ABC and in graph 2 we have ABC. That means in union graphs you have some of these things in there.
Yeah, so it is not compulsory that the both vertices should have the same name, because if you look at the first G1, we have E as a vertex, but then in G2 we don't have E. Similarly, we have F as a vertex in G2, but we don't have F in G1. So
okay, so sir, in this case, sir, so
hello.
In this case, so I'm saying that in this case, we are applying the concept of union in what's the name, in numbers, because
exactly
some are not actually the same. So we will name that one, but with those that are the same, we apply the concept of unions in numbers.
Exactly.
All right, thank you, sir.
Yeah. All right. Right. So without further questions, let's move on and talk about graph representation. I'm very sure all of us are familiar with this, so I'll just talk about it fast, and then we move on. So we have actually two ways of representing graphs, and one of them is the adjacency list, and then we have the matrices as well. So the adjacency list basically means that for every vertex, we list the adjacency vertices that are connected to it. And so therefore, if you look at the graph that's being given to us here, this graph, for instance, and we take vertex A, its adjacent vertices are B, C, and E. So we list them over there. We take vertex B, its adjacency vertices is just A, so we list it. The same thing applies to, this is C, which has vertices A, D, E, and then D as well. So we list them this way to represent this particular graph. And so you can be given the adjacency list and asked to draw the graph from it. And I believe that's going to be very easy. So this is how I represent graphs in adjacency list. You take each vertex and then you write its adjacency matrices just next to it, and then you are good to go. I hope there are no questions on this. Hello.
Yes, but what I want to know is that it looks similar to the neighbors, like the neighbor, how we find the neighbors of
exactly. So what are the neighbors of A? That is B and then C. So you write them down. B, C, and E. You write them down.
Okay.
And then the technical term is adjacency matrix. That's all. Instead of neighbors,
Instead of the
matrix.
neighbors, yeah.
Okay. Yeah. All right. Prince, your hand is up. Oh, you just spoke. All right, so let's move on. So this is an example graph that you might want to try your hands on. This is a very complex one with various loops around, and this is also directed graph. So please, the way you represent the adjacency list in undirected graph is quite different from the way you do for directed graph, because the neighbors are going to be different from each other. So please notice them very well. Those that move from A to B are supposed to be considered. So for instance, if you take this particular vertex A over here, we consider the out degree as the vertices that we will list to form the adjacency list of that particular vertex. So if you take A, for instance, we have B, C, D, and E as its adjacency matrix, or we can say the terminal vertices. So from A, there's an arrow to B, so we list it as part of it. From A, there's an arrow to C, so we list it as well. From A, there's an arrow to D. We do the same, and then from A, there's an arrow to E, so we have its matrix represented as this. Right, and then we can do the same for the others as well. Please, are we clear? And remember here we have the C, for instance. We have ACE because of the loop in the it basically refers to it, so we have to include that in it. Mind, this is not a set. This is a list, and a list can contain duplicate values or whatever it is. All right, so let's proceed to the matrices as well. So all this English, I will not read it, but then the simple explanation is that if you are given a graph and asked to represent it as adjacency matrices, you take the vertices, you number them on top of you number them as rows and then as columns. And then you do the connection from A to A. Do we have a connection between A and itself? If there is none, you represent that with a 0.
Come find your screen also.
It's the same for everybody.
Yes, sir.
Yes, it's off. The screen is off.
All right, let me rejoin again and then we continue. I mean, reshare the screen. Is it clear now, or is it showing now?
Yes, sir. It's showing.
All right, so as I was saying earlier, you take each of the vertices, you number them as rows and columns, and then you try to do the connection of them. So we have 4 vertices over here. So you just draw a table, and then you have vertex A, B, and then C and D. And equally you have A, B, C, and then D. So you have this. And now since this is A, do we have a connection from A to A? There's no loop to A, so you represent that as 0. Then you take A to B. Do we have a connection from A to B? That is true. Then you represent that with a 1. Do you have connection from A to C? That is true. So you represent that with a 1 as well. Do you have connection from A to D? That is true. Represent that as 1. Now move on to B. Do you have B to A? Yes. So you represent as 1 here. Do you have B to B? That is 0. Do you have B to C? That is 1. Do you have B to D? That is also 0. Right. So you do this until you've done that for all the vertices, and then you are good to go. And you have to also notice that if there are directions on the edges, it is different from the way you represent it with undirected graph. I think I have an example over here. So this is an example. No, this is not directed, but then this is an example that we can get as well. So we have A. So we have A over here.
The screen is off.
I don't know what's happening right now. Let me share the screen again. I hope it's clear now. I mean, it's showing now. So we do that and then realize that from this is
hello.
Hello.
Yeah, sir. It's showing now. Initially, we didn't see anything.
Oh, okay. Okay. Thank you.
So please, are you going all over? Are you starting this one?
Yeah, I'm starting over this one.
Okay.
I'm starting over. All right. So now these are the various row, and these are, I mean, the column, and these are the rows. So A, B, C, D here. And now we consider A and then A. Do we have any link from A to A? There's no loop over here. So that is why we have a 0 over here. And now we have A and B. we have A and B. Do we have connection from A and B? Yes, but then there are three of them. We have, this is 1, the middle one is 2, then the outer one upwards is also 3. That is why we have 3 over here, right? And then we have A and C. We have A to C, that is 0. And we have A to D, that is also 2. We have 1 here. And then we have 2 here. That is why this is 2. We have 2. Please, that we are clear. What we call graph isomorphism.
Your screen has been on and off. Right now, it's even off.
No, please, it's on. No, it's on. Maybe it's your end.
It's off.
I can't see it from here. It's off, not his end only.
It's off. It's off.
It's also locked here.
It's off.
Off here.
It's off.
It's on for some of us. It's on
It's
for some of
network
us.
issue.
Okay, then it's network.
All right, so those of you who can see it, are you seeing graph isomorphism
Yes,
or
we can see
adjacent
very well.
symmetries?
Hey, then what is happening?
Those having their phone.
Well, mine is now off.
Yes, we are supposed to see graph isomorphism.
Is it because of us are below the sea level?
I can see. I can see, sir.
I can't see him.
I think majority of us.
You see, because you're supposed to see graph isomorphism. All right, so let's talk about the graph isomorphism, and by definition, the simple graph that can be given.
Hello,
as,
sir.
Hello.
Please, I think majority of us. Okay, I think it's back on. It's back on.
Yeah.
It's back on. Back now.
All right, so when we talk about graph isomorphism, what we basically means is that if there is a one-to-one and onto function from f, from v1 to, let's say, v2, with the property that a and b are adjacent in g1, and if only if f of a and f of b are adjacent in g2.
Sir, please, it's gone off.
It's off
Sir,
again.
it's gone off. So if you can please disconnect and then reconnect so that we see.
All right, I'll do that.
I think it's your end, or you rejoin. You connect and.
Yeah, because I can also see.
Should we change
It's your end.
the platform that we are using? Should we change the platform?
You guys also check your network because some of us can see.
No,
I suggest
majority can also
better.
Me, I've rejoined like 3 times, but they still empty.
All right, let me reshare this.
Mine is on and I can see.
Kokuapana, are you below the sea level?
Anairi Anairi.
Hey, what's up?
Is it showing now?
Yes, sir.
Yes.
All right, so I will skip reading the mathematical definitions of graph isomorphism and talk about layman's understanding, how we can understand that. So basically, when we talk about graph isomorphism, it basically means that two graphs can be isomorphic if they can be relabeled. I mean, the vertices can be relabeled to get the other. In the next sense, we could see that they have the same structure, just that there are labeling differences in them. So basically, if you are able to restructure one graph to get the other, then you could say that those two graphs are isomorphic. Please, are we clear? If you are given a graph and asked to determine if one is or both of them are isomorphic, basically means that you can label the graph to get the other one, or you can label the second to get the first, or the first to get the second. Then we could say that yes, this is an isomorphic, or these two graphs happens to be isomorphic. So we say that they are structurally identical, even though their vertex labels are quite different. So example is what we are seeing on the screen here. So these two graphs, we can be asked to show or to tell if they are isomorphic or not. Is that clear? So who can actually tell us, are these isomorphic or they are not isomorphic based on the definition I gave? We can relabel them to get the other one. Yes, I'm waiting. The vertex naming are different, but then structurally they can be the same. Just the vertices that we labeled are quite different.
So they are isomorphic.
Why do you have any reason to explain?
Yeah man.
Explain.
So yes, so the reason I'm saying that is that for the first one we have is it, I'm not seeing the screen. Is it V1 and V2?
U1 and U2. The first ones are labeled U and the second ones are V.
Okay, so U1 and U2 on the first diagram is equivalent to V1 and V4 on the second diagram. I don't know whether I'm seeing it clearly. V1 and V4. U1 and U2 is the same as V1 and V4. And then
so you mean this?
Yes.
Okay.
Yes, and then U2 and U3. U2 and U3.
U2 and U3.
I'm coming. No. So U3 and U4. U3 and U4 is the same as is the same as V3 and V2. It's the same as V3 and V2.
Please, do you understand what? So in other words, if we are trying to relabel this one, we are definitely going to get the same one at the top. Or let me just say in a layman's term, this is more like two triangles facing each other. So if we are to construct a rectangle, a square from this, you're going to get a square from it, and that is why we say they are isomorphic. But if you are not able to reconstruct to get the previous shape, then we cannot say they are isomorphic. So we can reconstruct this to get this particular square over here, or we can reconstruct the square to get these particular triangles facing each other. In that scenario, we could say that yes, the two graphs are isomorphic. Please, are we clear? All right, so
no,
moving
sir.
on, we have some examples here. All right, so we have this.
Naomi.
So we have this one over here as two triangles facing each other, and we have the first one to be a square, square, right? To be a square. So now isomorphism basically means that when you reconstruct any of the graph that is given to you, you're supposed to get one of the other. So assume you want to reconstruct this to this form. Is it possible or not? If it is possible, then these two graphs are isomorphic. If it is not possible, then these two graphs are not isomorphic. And that is what I think Walense or someone just walked us through. So if you are trying to reconstruct this, we are definitely going to get the square as the previous one here. And therefore, these two graphs are isomorphic. Please, are we clear? All right, so let's move on to some more examples over here. So we have this example 2. And we are asked to show that the two graphs are isomorphic. Are they isomorphic or they are not isomorphic? Right, so we have another one over here as well. Still the following two graphs as whether they are isomorphic or not. And then we have some other ones here as well. We can also consider. But then there's a pattern in this. I would like you to go and look out for them, especially when we are talking about the terminology, the degree of the graph, I mean the degree of vertices, the neighbors, and all those stuffs. If you know those ones, it will be easy for you to be able to determine that these two graphs are isomorphic or they are not isomorphic. So please just go back, revise on the degree of vertices, the neighbors, and then see how you can relate it to the isomorphic graphs. Because if you look at this one, for instance, you can realize there's some relationship between the degree of vertices and the rest for each of the graphs. And that can help you to understand whether some graphs are isomorphic or they are not isomorphic. Please, are we clear? And these are some examples as well that you can consider as well. Is any question before we talk about the Hamilton graph? Is any question? We can move on. Okay. So when we basically talk about Hamilton graph, we are talking about a graph which has a close walk in connected graph, and then which passes each and every vertex of the graph exactly once, except the root vertex or starting vertex. Then the graph is known as a Hamilton graph. And in layman's term, basically means that if you want to walk through a Hamilton graph, you have to go through each vertex exactly once, and then except for the starting vertex. So when you're able to pass through a graph which has vertices once, then we could see that that is an example of a Hamiltonian graph. And then one thing you have to notice is that it is supposed to be a connected graph, and in most cases it's a circle. So you move from one, which is the starting node or starting vertex, and you visit each of the vertices at least once. Then we could see that that is an example of a Hamilton graph, and it's an example that we can understand from here. And in the example that is given above, we can realize that A, B, C, D, E, F is a closed or connected graph. And except for the vertices, which is the starting vertex, the graph passes through every vertex of the graph exactly once. And then at the time of work, the edges are not repeated. So you can't repeat the edges as well. So you have to go through one edge at once, and you can't repeat the edges as well. And due to these reasons, we can see that the graph is a Hamilton graph. Please, are we clear? So you can be given a graph and asked to identify whether it is a Hamilton graph or it's not a Hamilton graph. And you have to follow all these basic principles here. So it should be a closed walk, or it should be a circuit or a circle. And exactly, you should be able to visit every vertex at least once. And also you can repeat the various edges that you have walked. And this is only applicable to the other vertex, not the starting vertex, and then you are good to go. So that is what Hamilton graph or circle or circuit basically is. And then this will lead us to what we call the Hamilton path. And this is basically a path that passes through each and every vertex of a graph only once. And in this path, the edges should not be repeated. So we are basically following the same principle that we deduced from the Hamilton graph. And in other words, if the connected graph contains a path with all the vertices of the graph, then this type of path is called the Hamilton path. An example is what we have over here. So if you're asked to determine if this graph have or has a Hamilton path, how do you identify that? Please, can you hear me? How do you identify that this particular graph has a Hamilton path? Right, so basically,
the first thing you should look out for is to make sure that all of them are connected.
Okay, so the graph should be a circuit. That is one. And then also you should be able to stand at one point, visit every vertex at least once. You don't repeat the edges, and then you come back to the starting vertex. So assuming that we are starting from E, and we can move to C, we can move to B, we can move to A, to D, and then to E. So that means that we have a Hamilton path in this one, because we've been able to walk through the entire graph, visiting each vertex at least once without repeating the edges. Right. And then another Hamilton path. I do think that we are starting from Henry.
Yes, sir. Please, my question is, does that mean that with the Hamilton graph, it's not necessary that you have to pass through all the paths?
Yes,
but the most important thing is that you would go to all the vertices, but not necessarily passing through all the paths.
Yes, exactly.
Okay.
So this particular path here, E to C, C to D and then D to E is not qualified to be a Hamilton path because we are unable to pass through some other vertices like A and B. I hope we are clear. So for Hamilton path, we should be able to go through or visit every vertex at least once. We don't have to repeat the paths or the edges, and that is all. So this, yes, there is a Hamilton path in this particular graph that is given to us. And so if you want to make things very clear for the examiner, you can draw the path for us. And to demonstrate that, you just remove this particular one here, and then the rest happens to be the Hamilton path because we are passing through all the vertices at least once. We are not repeating any of the edges. Then can we also determine that there's a Hamilton path in this? Is it possible? Do we have one?
Yes, please.
All right, so obviously this is not even a Hamilton circle because it's supposed to be closed. However, this is not a closed or a complete, so we can't even move further to say this is a Hamilton circle to talk about finding a path in it. So this doesn't qualify to be a Hamilton circle. So we can't even find a Hamilton path in it. Is that we are clear? All right, so let's move on to this one as well. So determine whether Elliot.
Yes, sir. So please, if only the path becomes a circle, then it is a Hamilton path, right? Or a Hamilton graph.
Yeah.
Okay, thank you.
All right, so can we find a path in this?
No, please, because it is not a Hamilton circle.
And if you can move through all of them at once. So if you take this from E to C, C to D, D to A, and then F, how about we haven't visited this particular one here? And if we try to visit this particular one, we are going to repeat the edges. And therefore, we cannot get a Hamilton path from this. So for a Hamilton circuit, which is similar to what we just spoke about, in a connected graph, if there is a path that passes each and every vertex of the graph only once, and after completing the work, return the starting vertex, then the type of work is called a circuit. So if we are able to move from one point and come back to the same point, then we can call that path as a Hamilton circuit. Or you can say a Hamilton circle. So it's either a circuit or a circle. So yes, I made a comment here. I think we can get a Hamilton path from here, right? So we have this to this, and then this, and then this, and then this. But then it is not a Hamilton circuit because we cannot go back to E. Please, are we clear?
Sir, please, your screen. Sir, please, your screen is not showing.
It's network. Okay. So let me reshare the screen and see. All right, so what we got here, I was saying that you cannot get a Hamilton path from here. You can actually get a Hamilton path, but not a Hamilton circuit, right? Because we can move from E down to D. So we start from here, we move to A, we move to B, we move to C, and then we move to D. We have been able to move from A, which is one vertex, and visited all the vertices in this particular graph that's given to us. So we have a Hamilton path, but we are talking about Hamilton circuit. However, this one, there's no path in this. There's no Hamilton path in this one here. And then for us to get a Hamilton circuit or a circle, it means that we start from a vertex, we need to come back to that same vertex. Then we have a Hamilton circuit. So please note the difference. We have Hamilton path and Hamilton circuit. So the circuit basically means that you start from a vertex, you go around all the other vertices exactly once in a graph, and then your ending point or your terminal becomes your starting. Then you have a Hamilton circuit. If that is not the case, then that becomes a Hamilton path. Please, I hope we are clear.
Sir, are you saying two things? Like I'm hearing circuit and I'm at the same time path.
Yes, I'm saying two things. They are both different. So we have the Hamilton path and then the Hamilton circuit. So what I'm saying is that the screen is off again. I don't know whether Zoom is having the problem, because if it was network issue, you wouldn't have been able to hear me. I hope you can see the screen now.
Yes, sir.
All right, so let me explain from here. So we have this one here as a graph that is being given to us, and we are asked to determine if we can find a Hamilton path in this particular graph. And yes, when we talk about path, we start from one point, and then we visit each of the vertices in the graph. We don't necessarily have to come back to where we started from. That makes a graph. So in this situation, for instance, if we start from E here, we can visit all the vertices in this graph, which is from E to A to B, B to C, and then C to D. This is a path for us. And before you can get a circuit or a circle, it means we have to go back to where we started and take that as our ending points. Do you understand the path here? Because we have example on the circuit. All right. So let's move on to the circuit. Understand? So this is an example. We are trying to determine, or we are asked to determine whether this graph contains a Hamilton circuit. This instance, not a path. So yes, we can get the Hamilton circuit from this, because when we start from E, when we start from when we start from E, we can move to C, we can move to B, we can move to A, we can move to D, and then we can come back to E as well. So this becomes a circuit or a circle, and we call that the Hamilton circuit or the Hamilton circle. However, in the solution given here, we started from A, and it will work the same way. So we start from A, so we start from A, now we move to B, we move to C, we go to E, we go to D, and then finally A. This gives us a circle, and that is qualified to be the Hamilton circuit or circle we are talking about. So the path is different from the circuit. So ideally, the circuit should be a connected graph where all the vertices are connected to at least one of the other. So this is an example. Can we determine if this graph contains a Hamilton circuit? Is it possible? All right, so this is not possible because when we start from E, we can move to A, to B, to C, and then to D. We couldn't come back to E because we are asked not to repeat the edges. So if we move D to A and we try to connect to E, we are going to repeat the edge. And that is not allowed. So we cannot get Hamilton circuit from this particular graph here. Is that we are clear? So these are some important notes that you need to consider in Hamilton graph. So if any graph has a Hamilton circuit, then it also has a Hamilton path. But the vice versa, in this case, is not possible. So if you have a Hamilton path, you cannot get a Hamilton circuit from it. But if you have a Hamilton circuit, you can get a Hamilton path from it. And also, with a given graph, you can get more than one Hamilton path and as well more than one Hamilton circuit. So these are some of the things you consider in the Hamilton graph structure. So how many, this is an example that we can consider, determining whether this graph is a Hamilton graph. Is it, who can help us? Yes, anybody?
Yeah, it is.
So where do you start? Depending on where you start, then you get it. So where do you start from? Walk us through this.
I started from B.
You start from B.
B to C. Yeah.
Okay.
B to C.
To C. Okay.
And to D.
And to D.
And to E, A, and then F.
E. Relax.
No.
E, A, and you're confusing everybody. Yeah, let's start all over.
It is not.
Organize your thoughts. It is not a Hamilton graph.
Yes, sir.
Please, can you? Okay. Anybody else? Do you think it's a Hamilton graph or not?
It is not.
Sir, it is not.
It is not.
Why?
Sir, because
really?
when you
okay.
when you start from the A, moving to B,
okay.
C, D, and then you move to F, when you are going back to A, which is repetition, and it is not allowed. You go back to E before you can go to the A before you can go to the E.
Yeah, so ideally we are not giving a starting point, so you can start from any of the vertices.
No, what I wanted to say is I'm not repeating the A. If you start from B, but I can visit all of them.
Sir.
Okay, so
you can visit all of them without going back, without repeating and
all right.
Sir.
Prince, walk us through. This is show working. Yeah.
I said when you move from B, you come to
okay, B to C,
and come
okay.
to C, and come to D.
So you come to D, okay.
F, A, and then E.
F, E, and then E. Okay.
And E.
Okay. All right.
I've not repeated any of them.
Abubakari.
Sir, yes, so exactly what you said. I wanted there's a path, but there's no circuit.
Yes.
Yeah, so I wanted
it has a path and a circuit. Both of them are
very important. We said
the circuit and the path.
We said a graph. Or relax, let's not confuse ourselves. The question is in the determine whether this graph is a Hamilton graph.
Good.
We'll say
So
yes.
is it a Hamilton graph or is not a Hamilton?
Yes.
All right. So it is a Hamilton graph, right?
Yes,
and
sir.
we have one path in it. Or do you have a circuit in it?
No,
Yes.
sir.
Do you have a circuit?
Yes,
No,
sir,
sir.
we have a circuit.
All right.
So it's a
Saying a
circuit.
circuit. Walk us through the circuit. Where is the circuit? Tell us.
There's no
As
circuit.
if I'm not seeing any circuit, but then please, please, who said there's a circuit? Can you help us get it from here?
Sir, so per my understanding of circuit, you made us to understand that once it is in a closure, then it's a circuit.
Okay.
And this is obviously because
but
compared to the other.
But a circuit should be able to visit every vertex before you can call it a Hamilton circuit. Maybe your network went off, so you didn't hear me clearly. And looking at this, we can't visit all the vertices. We cannot visit all the vertices over here without repeating an edge, which will basically disqualify this to be a Hamilton graph or circuit in our instance. So we have a Hamilton path, all right, but then we don't have a Hamilton circuit. But remember, we said something here that in a Hamilton circuit, you can get a path in it. But in a Hamilton path, you can't get a circuit in it. So we are able to determine a path here, but then we can't get a circuit from this. Please, are we clear? Abubakari.
What I want you to emphasize is, so when they ask whether it's a Hamiltonian graph or not, it depends whether if it has either the path or the circuit, the graph is still a Hamiltonian graph, right?
Yeah. So are you able to move from one vertex to the other? All of them without repeating the edge? Yes, it becomes Hamilton graph, and that is what we just did earlier.
Okay, sir.
Yeah. All right, so this is another example that you can consider, and this is also another example that you can consider
Hello,
as well.
sir.
And so many.
Hello, sir.
Naomi.
Yeah, I want to be clear here. With the graph, does it mean when the question is posed concerning the graph, should we consider both the circuit and the path, or are we looking at only the path? I mean, when it comes with a graph, like the example that came before this very one, it was asking us, yeah.
Yes, the question was more like determine whether this graph is a Hamilton graph, right? And we learned earlier that for a Hamilton graph, you should be able to move from one point and visit all the other vertices without repeating an edge. So if you found that in here, then this becomes a Hamilton graph. And we're able to find that here.
So your network is gone. We can't hear anything.
We go to C, we go to B, and then very clear.
So you went off.
Okay, so what I was saying is that we are asked to determine whether this graph is a Hamilton graph, right? And for a Hamilton graph, we said you have to be able to move from one point, which is the starting point, and visit all the various vertices on the graph. Then that becomes a Hamilton graph. So yes, when we start from B, we can move to C, D, F, A, and then E. We have visited all the vertices without repeating any of the edge. So this becomes a Hamilton graph. But then can be further asked, can you still find Hamilton path or Hamilton circuit in this? Then you can move further and see if the path that you have identified, do you go back to where you started? If you are not able to go back to where you started, then it means that that is not a circuit. It is just a path. And we're able to identify only a path from here and not a circuit. So yeah, this is a Hamilton graph with only Hamilton path. All right, thank you so much. So now we can move on to this one here. Determine whether this graph is a Hamilton graph, which I think obviously this is not a Hamilton graph, but then you can try. If it is, you tell us. This is another example that you can consider, and then also some examples as well. Now let's move on to some other one here, which is Euler graph. Please, can you see the screen? I think it just went off.
No, sir, it's not changing.
It's off.
Let me rejoin again. I mean, reshare the screen again. Please, is it showing now?
Yes, sir.
All right, so I hope from basic school you know what an Euler is. Or you don't know? Can anybody help us understand what Euler
No, sir.
is?
No, sir.
E-U-L-E-R. Hey, nobody.
Oh yeah.
You didn't like going to math class. Eh?
My first time of hearing
Anybody
the
to
word.
help us? Hey, oh, you didn't like going to math class. That is why.
No, some of us, the school we went, we can't learn this.
All right. So we said earlier that Hamilton. All right, so we said earlier that Hamilton uses the vertex or it visits only one vertex. So the Euler is the opposite. It visits the edges exactly once. So the opposite of the Euler graph is the Euler graph is the Hamilton graph. So if all vertices of any connected graph have an even degree, and this type of graph is known as the Euler graph. That is one of the characteristics. So if the graph has 6 vertices, and all the 6 vertices has the same degree, then we could say that that is an Euler graph. And this graph shows that just a minute.
I can't hear anything. No. Hey, I'm not the only person.
Please, can you hear me now?
No, you are not. You are not. Yes, sir, we can hear you.
Am I Euler graph? The degree of vertices should be the same. So A has 2 degree of vertices, B has 2 degree of vertices, C has 2 degree of vertices. The same applies to E and then D. Then we could say that this is an Euler graph, right?
Hey,
Moving on,
I didn't hear
said
that.
that for Hamilton,
you were off.
Please, can you hear me now?
Yeah, I can hear you now. But what you explain, I didn't hear anything. No, it just came now. You circle all the distance. So I didn't hear it.
All right, so let me
I didn't hear the explanation.
Let me go over again. So,
okay, thank you.
The circles just indicate that each vertex has exactly the same degree, right? So the vertex B has degree of 2, similar to A, C, E, and then D. So if you have such scenario where the degree of vertices are the same for all the vertices, then we could say that this is an Euler graph. Please, are we clear? So to determine if one graph is Euler basically means that check the degree of the vertices. If they're the same for all, it is an Euler graph. Now moving on, we spoke about Hamilton path. So Hamilton path uses the vertices. You must visit all the vertices, or all the vertices must be present in the path. That is Hamilton path. But then when we are considering the Euler path, it means that all the edges must be present in the path. Then we can say that this is an Euler path. So Hamilton considers the vertices, and then the Euler considers the edges. And as we said earlier for the Hamilton, you pass each vertex once. The same way apply the Euler path edge of the graph only once, then the type of path will be called the Euler path. So if you pass through the edge at least once or only once, then that qualifies to be an Euler path. This is the exact opposite of what the Hamilton was telling us. All right, so we are giving an example. Determine whether this graph contains an Euler path. Does this graph contain an Euler path?
Yes.
It does.
Yes.
So walk us through.
Yes.
How do we get it?
Because
where do we start?
Like, I started from A and moved to B, C, and then D, and then C. That's all. Go. And also, I also use the principle of them having an even lines, you know. Oh, yeah, that is 2, 2. Each of them should connect to 2, 2. So when you take the A is connected to A, B, and then D, and then
I didn't get it. So A, B, C, and then D.
Then they are not the same.
A is connected.
Please, can you read again? My network just...
I said A is connected to A, B, and then B, and then
so A to B.
Yes. And then A to D.
And then
if you take C to C is also connected to D. Hello.
Let's get a path. Let's get a path from it. So just walk us through the path from this vertex to this vertex to this vertex.
Oh, for the vectors is A, B, D, and then C.
A, B,
Wow.
D, and then C.
And then C.
Okay. But then we said earlier that we have to pass through every edge. So we are missing this and then this.
Can do.
Right, so this is what the Euler path. D, ambassador is.
If we move.
Ambassador, your hand is up.
Yes, sir. Sir. Sir.
So we have and we go to
yes,
B, and then we C, and then we go to B. Did we get it? So we are considering that all the edges must be part of the path that we are supposed to draw. If that's the case, then there is an Euler path. So from D to A, and then A to B, B to D, and then C to B. Please, with this situation, we can repeat the vertices, but not the edges. That is why we have two D's and then two D's in there. But then the edges are not repeated, just the vertices that are repeated. Right, so this is some more examples that you can consider to try. And we have the Euler path as D, A, B, E, D, F, E, C, and D. Well, let's see.
Yeah, man. So the Euler path, we are saying that yes, but the meaning that you gave, if you can kindly go back. The meaning, it says you should have the same number, each vertex you have the same number of path. Then I don't know if I stand to be corrected. Please, can you scroll back a little bit? I want to talk to that slide.
Yeah.
So hello. Hello.
We can hear you. You talk. Oh.
Sir.
The screen is not showing. The screen is no longer showing.
And I hear you.
You can speak. Speak. Guys are here. They will help you out. Speak.
So per the slide that said displayed, the meaning of the Euler path, it means each vertex should have the same number of each vertex should have the same number of edges connecting to it. Each vertex that you pick, I stand to be corrected. But if you compare that definition to this particular question given, determine whether the graph contains an Euler path. I don't really get the two.
All right, so let me explain it here. So we have the Euler path and then the Euler graph itself. So a graph can be considered an Euler graph if the degree of vertices for each of the vertices are the same.
Sir, we can't hear. The network went off. Okay, so
yeah. So what I'm saying is that we have Euler path and Euler graph, right? So the Euler graph basically means that all the vertices must have the same number of edges connecting to all of them. So that is what we saw over here. So this is an example here. So for B, we have only 2 edges connecting to it. For A, 2 edges. For C, we also have 2 edges connecting to it. And then E and D the same way. So if there is an instance like that, then we could say that that is an Euler, graph. But when we're talking about the path, it means that we are moving from one point throughout the entire graph, making sure that all the edges are passed through at least once. And that is what we have over here. So we have from D to A, the first edge, we pass through that. And then A to B, that is the second edge. B to D, that is the second edge. B to C, third edge. And then C to D, that is the fourth edge. So that is that for the path called the Euler path in this particular graph. We don't care if we pass through the vertices twice or 3 times. Only what we care is that the edges must be passed through at least, once, not at least. And this one was able to satisfy that. You realize that we didn't pass through any of them. All of them. Please, are we clear? Any question? Right, I think you can move on. So these are examples that we can solve. So for this Euler graph given, this is the Euler graph. Apanakwaku.
So I have a question to ask on the other graph. Like, not this one.
Okay. This one. You mean this?
Yes. No, the other one.
Which other one? This one here.
Yes. Yeah, this one. It seems the B is having 2 connect paths. That 3 paths. That A, B, and then B, D, and then B, C.
Yeah. Yeah, so all of the paths are included here. So we have this, which is D to A, and then A to B, B to D, D to C, and then C to B. All the paths in this graph are connected. So that is the Euler path we are talking about. So you can pass through the vertices as many as you want, but then the edges, you should pass through it once.
Okay.
All right. And this is another example that you can consider with this path here. So this Euler circuit is similar to the Euler graph that we saw earlier. Euler circuit that we saw earlier. So if all the edges are included and forms a circle, then that becomes the Euler circuit. Please, are we clear? So that is what this particular English is talking about. So if you're able to walk from one vertex throughout all the edges to the starting vertex again, then we have the Euler circuit. And this is an example that we can consider. So determine whether this is an Euler circuit. Can we move from A, visit all the edges, and come back to A? If that is possible, then we can say that that is an Euler circuit. If that's not possible, then we can move on and say it is not an Euler circuit. And then we have this one as well. Do we have an Euler circuit from this? If you can move from maybe A through all the various edges and come back to A, then you can also say that that is an example of an Euler circuit or an Euler circle. Please be clear. And then we have another thing we call the semi-Euler graph. And that one, if there's a connected graph that does not have an Euler circuit, but it has an Euler path, then that type of graph will be known as the semi-Euler graph. So if we don't have a circuit, but then we have a path, then that is an example of a semi-Euler graph. And then any of the graphs will be considered the semi-Euler graph if these conditions are met. So for this, the graph must be connected. The graph should be connected, and the graph must contain an Euler path. So if you have a graph that is connected and has an Euler path, then we could see that this is a semi-Euler graph. So we have an example here that we can talk about. So this has an Euler path, but it doesn't have an Euler circuit. So yes, this is a semi-Euler graph. Please, are we clear? So these are some important notes that you need to consider for Euler graph. So if there is a connected graph with an Euler circuit, then the type of graph will be an Euler graph. An Euler graph with connected circuit or an Euler circuit, then that type of graph will be an Euler graph. And then if there is an even degree for all the vertices of the graph, then that type of graph will be an Euler graph as well. And then if there is an Euler graph, then that graph will surely be a semi-Euler graph. And then also, it is not compulsory that the semi-Euler graph is also an Euler graph. So if you have a semi-Euler graph, it doesn't necessarily mean that it is an Euler graph. But then these conditions must be met, or if they are met, then you can say that you have an Euler graph. The degrees must be the same. Then if there's an Euler graph as well. So these are some examples that you may consider, determine whether this graph is an Euler graph. And yes, this is the graph that we have from it. We have determined whether this graph is also an Euler graph. So these are other notes that we can also talk about. And I think these ones are reading, so you can just go and read all of them. We have some other here. And then we have some real-time application of graphs. So for social media analysis, it is very important. Network monitoring, financial trading, and, Internet of Things management, autonomous vehicles, and disease surveillance. Please, any question? Is there any question? Can you hear me? Any question?
Yes, sir.
All right, so we are supposed to do the heaps data structure as well, but it's not difficult. I guess you can read it and then understand. It's just 15 slides. I don't know. Can we continue, or we should just close it? Probably, if you have time, we can schedule a meeting at convenient time for all of us, and then we do it. Just 15 slides.
We don't know. Some have lectures. I don't know the time. If it's longer, we will just continue and finish. But I don't know the time.
Maybe just some 20 minutes, we'll be done with the heaps. They are not difficult to understand. Do we have any class in the next 20 minutes?
It's 11:50.
We have class in the next 50 minutes.
50. So can we proceed, or we should wait for you to go and prepare for that class?
But I think 20 minutes you can use to brush through so that we get it.
Let's just finish it.
We are not going to meet again.
Okay, all right. Thank you so much. Hope the screen is showing now, or is showing. All right, so this is heaps data structure. And this is what we are supposed to know. The types of heap data structure, properties, some operations that we can perform on them, advantages, disadvantages, and we talk about some applications as well. So by heap, it's just a binary tree-based data structure that follows what we call a heap property. And in a heap, the value of each node is compared to the value of 8 children in a specific way. And then those specific ways happens to be the types of heaps that we have. So I'll just keep this one and then move on to the types of heap and try to understand it. So we have the max heap, as we saw, as the ways to compare the various children. And then we have the min heap as well. So the max heap, the root node contains the maximum value. And as we saw from trees previously, we have the root node, and we have 8 children, and the other node as well to the leaf node. So the root node of a max heap has the maximum value. And the min heap does the reverse. The root node contains the minimum value, and the value increases as you move down the tree. And it is the total number of comparison that is required in the max heap or the min heap is according to the height of a tree from last week's lecture. And the height of the complete binary tree is where n happens to be the value for the height of the tree. So in case the height of the tree is maybe 5, then we could equally say that the time complexity for that particular max heap or min heap is big O of log 2 or log 5 or log 3. All right, so this is what we have. So what we are seeing to the left is the min heap, and what we are seeing to the right is the max heap. So you see that the root has the least value, and then the value keeps increasing as we move downwards. That is what the max min heap does. And the max heap, the root has the highest value, and as we move further, we have the least as well. So in most cases, the leaf node has the least values in a max heap, and the opposite is true for the min heap. So these are some of the properties that we can identify from a a heap data structure. So it's a complete binary tree, and level. All the levels of the tree are fully filled except possibly the last level, which is filled from left to right. And this property ensures that the tree is sufficiently represented using arrays. And we also have the heap property. This property ensures that the minimum or the maximum element is always at the root of the tree according to the type of heap that we spoke about just some few slides ago. Then it has a parent-child relationship. So the relation between a parent So these are some of the properties that we can talk about: the heap property, the parent-child property, and the complete binary tree structure. All right, so moving on, we can talk about some other properties such as efficient insertion and removal. So if you want to insert and remove operations in heap are quite efficient. And new elements are inserted at the next available position in the bottom right left. And the heap property is restored by comparing element with the parent and then reswapping it if necessary. And also provide efficient access to external elements. This is because the minimum or the maximum element is always at the root of the heap, which allows for a constant time access. That is big O of one notation. Then for complexity. I have some very important concept that we need to understand, which is called the heapify. And in this process, it's used to rearrange the element to maintain the proper heap data structure. That is, if we insert a value, how do we make sure that we follow the type of heap that we are actually using? And that is why we need to perform the heapify operations to do that. And then this is done when we insert a node and it creates an imbalance in the heap due to some operations on that node, that is insertion or deletion. And at this point, the time complexity is big O of log n just to be able to balance the tree structure. And for max heap data structure, it balances such a way that the maximum element is at the root of the binary tree and the minimum in such a way that the minimum element is at the root of that binary tree. All right, so let's look at some operations we can perform. We can perform insertion, that is, we insert new elements into the heap. And then since we are adding a new element to the heap, it will obviously distort the heap data structure, regardless of which one we are trying to use. So it is very important that we perform the heapify operation to maintain the property of the heap that we are trying to use. Either it's a max heap or it's a min heap to maintain the structure. So assuming this is an example here, we have this example at the top. This is the current heap that we have, and it's been implemented using the max heap, right? And on the second one, we are trying to insert a value into the heap data structure. Let me use a different color here. We are trying to insert the value into the heap data structure we identified earlier, and the value is 10. Now we are using the max heap, and we said earlier that we need to insert the value next to the available slots to the left. So we have 5 over here, which is empty. To maintain the structure, we add it here, which is 10. But since we are using the max heap, we need to compare the child and the parent to establish the relationship to be able to balance the heap data structure. So since a max heap, you compare the parent, which is 5, plus the child, which is 10. Which one is greater? Obviously 10 is greater, so we have to swap their positions. So now we get 8 here, and then 5 is going to be here. Now we are done, but we still need to compare this and this to see if there's any difference in them. So you compare the first root to each child, this, which is 10. Sorry, we're supposed to insert 10. So 8 and 10 is going to be that 8 is less than 10. So we have to now switch or swap the positions of 8 and 10. And now after the heapifier, this is what we have. So we have 10, 4, 8, 1, 2, 3 to balance the structure. So that's how the heapifier basically works. When you insert, it comes to the bottom, and then you have to now compare the parent and child to see the relationship between them to balance the heap data structure. Please, I hope we are following. All right, so I'll just finish in the next 5 minutes, and then you ask the questions that you have. So this is inserting into the heap data structure and trying to balance it based on the type of heap we are using. Here we are using the max heap. And now we can equally perform deletion on the heap as well. So if we delete an element from the heap, it always delete the root element of the tree and replace it with the last element of the tree. So since we delete the root element from the heap, it will distort the properties of the heap that we have established. We need to perform a heapifier again. And for time complexity, it is big of log n. That is the height, where n is the height of the tree. This is an example that we can consider. So we have the initial heap over here, and then we are trying to delete a value from it. So when we delete, we said earlier, this, we are deleting 15. When we delete, automatically is the root that deletes. So after that, it is the last node that will now take place of the root. That is why we are seeing 3 as the root over here. And then it was the last that we inserted. Now we need to perform heapify, now structure the heap very well to meet what we are doing, which is the max heap. So now what we have to do now is to compare the parent and the child. Right, so parent is 3 at this point, child is 7. But since we are dealing with max heap, 3 is less than 7, so we swap their positions, and now we have this one here. So now the heap is well positioned based on the properties and the type of heap that we are using, which is the max heap. So this is how the operation is done. When we delete, automatically it is the root that deletes. So to restructure it, we need to use a heapify to do that. And then some operations that we can perform include the get max for max heap or get min for min heap. And then let's find the maximum element or minimum element for max heap and then the min heap respectively. So if you want to get the maximum element, you use the get max to get a maximum element. But then you should be working with the max heap to use this get max. And then also get min for min heap as well. And equally we have the remove min, remove max. And this operation returns the delete and deletes the maximum element and minimum element from the max heap and the min heap data structure respectively. And just to make it simple, it deletes the root element from the heap, binary heap that you have implemented. Right, and these are some advantages that we can talk about. It has fast time access, as I said earlier. The notation is big O of 1, which is a constant time, and it's most desired in most other applications because that is the best time complexity you could ever have. And it also has efficient insertion and deletion operation because it is from the top. it makes it easy for us to delete or insert as well. And then for flexible sizing also, if you have less data to store, you can go in for the max, for the heap data structure. And then it can be easily implemented when we are trying to use in array. So in array data structure, you can easily implement the heap data structure. And then for real-time applications, this is quite good for that. And these are some of the disadvantages that we can talk about. Not suitable for searching of elements. So if you want to search for elements, then it is quite not suitable for them, except for the fact that you want max, min, and all those stuff, which will give you the notation of big O of n notation. And then you also need extra memory overhead to maintain the heap data structure, because when you delete, you need more memory to temporarily store the values and then try to perform the heapify operation on them. And then it's also slower than other data structures like arrays and linked lists for non-priority queue operations. So these are some disadvantages, and these are some applications as well. So if you want to implement priority queues, you can use a heap data structure for that. And these are some of the operations that can perform: insert, delete, extract maximum value, and operation is big O of log n. And if you have a system that's will have to be implemented in binomial heaps or binomial system of Fibonacci, you can even go for heaps as well, because we have the binomial heap and Fibonacci heaps, which are some variations of the binary heap. And they perform unions also in big O of n time, which is big O of n operation in the binary heap. And then also for other statistics. And the heap data structure can be used to efficiently and effectively find the kth smallest or largest element in an array, just as I said earlier, using the get max for max heap and using the get min for min heap. All right, so I think that is basically all. So if you have any questions, you can ask, and then I'll clarify them, especially with this particular part. Do you have any question? Do you have any questions to ask?
Yeah, so this one is the maximum one, the maximum heap.
Yeah.
Where the root has the higher value.
Exactly.
So what of in the case of the mean heap?
Okay, so let me see if I can draw some example of the mean heap. So we have the mean heap, let's say 5 as the root, and then we have 10. We have, let's say, so we have 10 here. We have let's see, and let's say this is 40. And then let's say this is 45. So please, can you ask the question? Do you mean the deletion or the insertion? So assuming this is the main heap that we have, right? Yes. And we want to perform a delete. So when we delete this one, when we delete, it is the top that will go.
All right.
Right? And the last value, which is 50, is going to take place of as the root.
Okay.
That is where we now, so keep the other one in mind. So this is now going to be 50. And this will not be there, right? So now what we have to do is to compare the child or the children and see which one is less. So 50 and 30, and then 50 and 40, which one is less?
30 is less.
So 30 will have to move up. Right, so 30 will be here.
Okay.
And then you get 50, and then you get 40. And now you have 50 and then 45. So obviously 45 and 50, 45 is less. So 45 will move to where 50 is, and then 50 will come back to where 45 is. So that the tree is going to be balanced properly based on the bin heap structure we are using.
Okay.
Yeah, that is how basically heaps really works. Is any other
this
question?
side is only the heapify that is a little bit confusing.
Yeah, so the issue is that when you delete, just notice when you delete, it is the root that is going to be deleted. And as soon as the root is deleted, it is the last element that will take place of the root. So let me use it. So when 15 was deleted, 3, which was last, now came as the root. But then we are dealing with the max heap, so we need to make sure the heap is balanced. So we compare the various relationship between the parent and the child. If it is max heap, you swap the positions accordingly, and then you do that for all the various elements until the tree is balanced. Now we move on.
Okay.
Yeah.
We'll try
Is
our
any,
hands on it.
all right, that will be fine. Any other question? Or if there are no questions, then
Papa.
I don't think he's here. Lazy has left us alone. All right, so I wish you all the best. And we meet again. You're welcome.
Yeah. Is it that you guys are asleep or you have left?
Can't you see we are tired? Can't you see?
Okay, we are tired. Enjoy. Man is tired, Charlie. Thank God this is the end of the course. Else I don't what we would have meet again there. Only God.
We have another lesson out here.
I'm done for the day.
Go and sleep.
We have closed or what? Hello.
Pana, you just wake up, eh?
It's really slow. Are we closing or?
We are done. We are done.
Okay. Then, man. Thank you. I'm gone.